So what's up, guys? I'm Ethan with Tendermint, and we were thinking since Tendermint's kind of marketing this whole private blockchain thing, selling out to banks, yada yada, and this is like a Bitcoin meetup, and you guys don't take very kindly to that, we thought we'd show you that we're actually still cool by performing a rap song about how great Bitcoin is. So unless there are any serious objections to this, I'm going to proceed with my cover of Biggie's Juicy. All right. So I'll throw the lyrics up. Yeah. This song is dedicated to all the economists that told us we never amount to nothing. To all the people that lived in the buildings that we were hustling in front of that called the SEC on us. When we was just trying to free money from his crypto beholders, corporate beholders, and all the devs in the struggle. You know what I'm saying? It was all a dream. I used to read Usenic's with crypto fiends, salting nonsense math like you never seen, writing algos on the wall. Every Saturday, hack attack, is it magic or a flaw? I let my trace route till I got no doubt. Phone and function Wi-Fi, listening on private routes. Way back when I had the private key in my lap and the hash to match. Remember Merkle proofs? Daha, you never thought that crypto would take it this far. But now we in the limelight, cause the price is right. Time to get paid, blow up, we're saving world trade. Born sinner, the opposite of a winner. Remember when it cost 10,000 for pizza dinner? Piece of Witness G, Marty Hellman, David Shaw, Finney and Merkle, Satoshi's never gone. We're blowing up like you thought we would. Hashing blocks and innovating cause we could. It's all good. And if you don't know, now you know. Crypto, you know very well who you are. Don't let them hold you down. Reach for the stars, the moon. You had to go, but not that many. You're the only one. I made the change from a common anarchist to up close and personal with the banking rich and vigilant. I'm checking SIGs with GPG all day. Son, my key is the crypto way. No way, the crypto life keeps me busy. Bankers used to diss me, now they play me close, think like they miss me. I never thought it could happen, this crypto stuff. I was too used to weapons export stuff. Now bankers play me close like Parasite play host. From the Bay Area straight through the East Coast. Companies on the scene pushing hypeware for weeks and sold out seats to hear Peter Todd speak. I'm living life without fear, putting 5 Bitcoin in my baby girl's ear. Lunches, brunches, interviews with mining pools. Considered a fool because I renounced the Keynesian school. Stereotype of a crypto dev misunderstood. And it's still all good. And if you don't know, now you know, crypto. You know very well who you are. Don't let them hold you down. Reach for the stars. You had to go, but not that many. Cause you're the only one who won. Cryptocurrency, no counterparty risk. When e-gold went down, man, I couldn't picture this. 50 petty hashes, money, orange open source, a few thousand nodes, and a big fat I told ya. Banking bill about 2 G's flat. No need to worry now that Bitcoin's got your back. And open source is lounging, celebrating every day, got everyone espousing. Thinking back on that spaghetti code hack, now we skirt capital controls, leaving fiat in the tracks, and we love to show it off, of course. Reddit circle jerks every time we up in Forbes. We used to fuss when the block size dissed us. Some feet can't wait till lightning picks up. And SegWit is the best shit, cause you can soft fork anything you wanted. Yeah, damn right I like the life I live, cause we went from pennies to hundreds and it's all good. Yeah. And if you don't know, now you know, crypto. You know very well who you are. Don't let them hold you down. Reach for the stars. You had to go, but not that many. Cause you're the only one, the one and true money. Yeah. Biggie Smalls. All right. I literally have plenty more where that came from. I'm not kidding. I don't think any are as good as that one, though.
That was the best performance as a Bitcoin dev.
All right, that's what I like to hear. So we're cool, right? Even though this is about private blockchains, we're still cool. Proof of stake, all that crap. That's why I did this. All right. I guess I'll go full screen here. Cool. What's up? F11. Nice try. Oh, the real F11.
Yeah.
Function. Okay. Anyways, Tendermint. So we're Tendermint. We're cool. We write sweet rap songs. We also do this thing with blockchains. You know, we let you build, deploy, manage them. And we bring simplicity, security, and speed to the world's blockchains. I don't know if you've noticed, but no one seems to understand blockchains. They're kind of super complicated. There's all kinds of issues related to security, and they're slow as shit. I mean, to be frank, like, you know, who wants to wait an hour to know that they moved money? I mean, it's better than banks, I'll give you that much. But we can go faster. And as much as I love Bitcoin, as you just saw, I think we can do better, and we'll talk about that. Okay, great. So just to put things in a little bit of context so that this isn't really coming out of nowhere. I mean, people see blockchains and they think like, oh, this is like totally out of nowhere, dropped out of the sky. Like, what does this have to do with anything? How do we understand it in the context of the history of computer science? So if we go back to the beginning, I mean, it all started with like siloed computers and single mainframes, and people had to like go across the street with their punch cards and put the thing in and get the result back the next day, right? It was horrible. But the point was everything was running on one machine. But over time, we got to this point where, you know, we needed things to be able to run on multiple machines so that we could have some fault tolerance, because computers suck. They crash, they die all the time. So if everything's on one machine, you could lose it all, right? So very naturally, we spread out into these distributed networks where we have certain replication algorithms that allow us to replicate data across many machines without losing it. And to do it in a way such that all the machines stay in sync, right? So that no matter which machine you're talking to, you get the same view of the data, right? And these are called consensus algorithms, and they've been around since the late 70s, basically, in many iterations. And it's a very well-developed science, the study of fault-tolerant distributed machines, right? And of course, it is pretty much culminated in something like Amazon, right? Which offers this hugely, highly available web service that anyone can use. And at the very bottom of Amazon's stack is a consensus algorithm that holds the pieces together, right? And no user sees that consensus algorithm, right? It's not like when you go to add something to your shopping cart, you have to wait for that item to get seen by Amazon's consensus. No, that would take forever, right? So they only use their consensus algorithm for the more important things, right? For like, you know, putting up new machines or for coordinating machines taking over some resources, things like this. And so the most common algorithm is something called Paxos, which was developed in the 90s, in the early 90s actually, but it wasn't published until much later because no one seemed to be able to understand it. And still today, you know, basically no one understands it, which motivated another algorithm called Raft that came out a couple years ago, where before Raft, the primary purpose of fault-tolerant algorithms was to be fault-tolerant, right? Raft decided, no, screw that. Our primary purpose is to be understandable, because if no one can understand it, they're not going to get it right. And they ended up coming up with a very beautiful algorithm that's quite easy to understand, that works very well, and is seeing tremendous adoption. And everyone is starting to build stuff on top of Raft, and it's really great. Right. But going back to the story, the natural evolution of things, you know, the problem with Amazon's big distributed service is that it's centralized and it's basically controlled by that guy, right? And no one really likes that guy. I mean, he's all right, but he's basically in charge of the whole thing. And so all the pieces are basically pawns of Jeff Bezos, right? And he can ultimately do whatever he wants with it. And so we don't like that. So there's sort of this natural next evolutionary step, which is to say, okay, we have these decentralized networks or distributed networks, but we need to create a political decentralization, right? So that no single bald-headed or otherwise individual owns the whole thing, right? And of course, the first instance of this was Bitcoin, and there have been further instances, Tendermint, Ethereum, and now we have Tendermint. And the idea here is that you don't just want to be tolerant to computers crashing, you want to be tolerant to computers exhibiting arbitrary behavior, which could include malicious behavior, right? And so such behavior we call Byzantine, you know, in tribute to the Byzantine generals trying to attack Rome and sort of not knowing, you know, is one of the generals a traitor? Is he actually working for Rome or not? And you can't really know just with you know, if there's only 3 generals and one of them is betraying the others can't figure that out because he could tell one thing and one another thing, and none of them can really figure out who's the liar, right? So you can sort of split the network. And so it turns out there's this fundamental result in this sort of Byzantine fault-tolerant theory that you need at least 4 machines to tolerate one down, right? And Bitcoin all these years has been like, oh, well, we can tolerate up to 50% malicious. But certain analyses actually show that even Bitcoin is susceptible to this, 1/3 fault tolerance model. Right. But the point I'm trying to make is that this move towards Byzantine fault tolerant systems is really just a natural progression in the evolution of consensus science, where we go from single machines to many machines owned by one person to many machines owned by many people. And that especially in sort of a post-Snowden era where no one really trusts anyone else and things are constantly subject to attacks and hacks, this kind of architecture makes a lot of sense. And we will see adoption of Byzantine fault-tolerant consensus on a wider scale with or without any talk about blockchains. But blockchains have dramatically hastened that because they add additional properties. And so, I like to say that when Satoshi introduced Bitcoin, he really did 2 things, right? There's 2 key innovations, and they often get confounded with each other. On the one hand, it was augmenting the idea of Byzantine fault tolerance with economic incentives. And in Bitcoin's case, it actually used only the economic incentives to motivate the consensus, right? So it was really an economic solution to the Byzantine fault-tolerant consensus problem. But over and above that, and to complement that and make it actually possible, he introduced a data structure that used Byzantine fault tolerance with Merkle trees, public key cryptography, and P2P networking. And that combination allowed him a very robust system where anyone could very easily verify any piece of the system, right? So using this combination of things, you have very lightweight, low-cost trust without having to trust anyone, right? And this is what everyone got so excited about. But what's happening now that we've sort of seen Bitcoin and are trying to sort of disentangle it and place it in the context of the history of computer science, we see that really there are these 2 pieces here. And that the economic component is absolutely critical for public systems, right? You need some kind of economics to motivate the system. But the other component, what I like to call the blockchain, right? The piece that is the Merkle trees, public key, P2P, and BFT, with or without the economic component, is going to be very useful to a lot of people, strictly from the perspective of this evolution of computer science, where untrusted or semi-trusted parties want to work together with a common platform without having to trust each other too much, right? And so what Tendermint is doing, and a number of other people, Eris and lots of other companies that are starting up now, is trying to take this underlying data structure, with or without the economics, and use it for businesses and banks and governments and so on to build on top of. And with that, I'm going to turn it over to Jay to talk about some of the components of Tendermint.
Hey, thanks for that. So I want to talk about what our mission is. Excuse me? Mike. Hello? 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 Great. I want to talk about why we're here and why we wake up in the morning and what we want to bring to the blockchain world. And it's really it's going back to like what Raft wanted to do to start with. We want to bring simplicity to the space. Everything is so complex. A lot of people are reinventing the wheel. Everybody has their own stack, and it's still going on. Everybody's building their own little siloed ecosystems, and there's just not enough coordination going on when we could be sharing a lot of the foundational pieces so that we can move ahead. And so what we're doing, and I'll show you, this is what we're going to show you tonight, is a new architecture for blockchains that we've been working on. And the reason why we created that architecture is to open up the tools, the engine, the pieces that we've created so that anybody can use them to create new systems, new blockchain applications. So, for example, if you want to, if you have a great idea for a new virtual machine, like an alternative to Ethereum, or if you have a better system than UTXO, don't just fork some blockchain stack. Use our architecture, and you'll see why. You'll see why it's a good idea. So we're creating a platform, and it's all about empowering applications. UTXO systems, the Ethereum virtual machine, those are all applications of blockchain technology. That's how we think of it. And so our platform is about empowering application development. Okay, so that's great, but it can't just be about simplicity. It has to be backed by something. So what is that thing that we're offering? Well, we're offering real security. We're offering security for 95, 99% of the use cases of blockchains. So, there's all kinds of, there's proof of work, which is dominated by Bitcoin. It's difficult to start another proof of work chain. So if you don't like how Bitcoin works, then you're kind of out of luck. Are there alternatives? That's a rhetorical question. The answer is yes. We created that alternative, and we want to share it with you so that everybody uses it. And the reason why is because people need different blockchain applications, and Bitcoin as just the central global blockchain isn't good enough, and everybody wants. We want to scale. We want to scale out horizontally. We want to run multiple applications. So how do we do that? We use a Byzantine fault-tolerant algorithm that we've developed for blockchains. And the reason why it gives you security is because of these three things. The first thing is the actors who are committing blocks in the system they're identified. They're pseudonymous or they are publicly identified, either way. They're not anonymous like Bitcoin miners. That's one. The second thing is we have this algorithm that guarantees that if a block gets committed and there's an attack of the system, so that there's a fork, say, for there to be an attack, you require at least 1/3, a significant portion of the validators to cause the attack. If everybody's working, just running the program, the protocol as they should, then this will never happen. But for there to be a disruption of the service, a significant portion of the nodes, the miners or the validators, need to attack it. They need to be hacked or they need to try to subvert the system. The third is, once there is such an attack, we can find out who had done it. So it's an accountable system. These three properties are not the same properties of Bitcoin. Right? Bitcoin does provide BFT, like security of a blockchain, but this is another system. It's an alternative system for blockchains. And it works for cryptocurrencies. It certainly works for private blockchains. It's, in fact, probably optimized. I'd say it's optimized for permissioned blockchain deployment. Another thing, so this is sort of, okay, so when I was working on this in like 2014 and iterating on the algorithm, one of the things that we realized is that it's actually significantly faster. Right? So for most purposes, you're going to have like 100 to 1,000 validators. If you have any more than that, it's kind of redundant. Like how many validators do you really need? But for those numbers of validators, we can get very fast commit times. If you look at Bitcoin, it's like 10 minutes to commit a block. That block may or may not get rolled back because it's a forkful system. And if you want to validate a larger transaction for, like you're moving millions of dollars, say, then you're going to have to wait for additional confirmations. That's not true in Tendermint. It's just a single block. You get it confirmed, and it's over. Right? And the reason why is because we don't use proof of work. We use a pub key-based system, and it's accountable. Ethereum is currently using proof of work, and they've got 17-second block times, which is great for applications, but it still doesn't provide the same properties as Tendermint. You still need to wait for additional confirmations to commit a block. And a lot of the applications benefit from having such a short commit time. Okay. This is Vitalik here talking about how that Ethereum or they underappreciated the need the desire to have faster block times. So it's not about block times, actually, it's about transaction committing. Right? So another property of Tendermint in our architecture is that it's very fast. The throughput in transactions of the system is amazing. It's a network-based protocol, and we'll get into it later. And it really depends on the application, but everything else that we provide for you is very fast. So if you design your application to be able to handle 10,000 transactions per second, say, on a single application or blockchain, the core will accommodate. I don't know what will happen if you put the EVM on it. It probably can't handle 10,000 transactions per second on a single blockchain with the EVM, but that's why we're developing this alternative system, so that you don't have to use the EVM. You can develop your smart contract in any language that you want that runs in bare metal, that uses a socket protocol, and it can run much faster. So we'll get into the architecture. Do you want to do it? Yeah.
Yeah, we figured we'd just keep switching up, keep you guys on your toes. So, question that comes up a lot is what's the relationship between Tendermint and Eris? And it's a useful question to explore because it illustrates how our architecture works and puts it in context, right? So the classic example is really WordPress and Apache, right? WordPress and Apache are two independent components that can work, either on their own or with other partners, but they're really great together, right? WordPress is this like application level platform. Apache is this server level platform you can build arbitrary applications on top of, right? And they communicate using a socket protocol. And you can swap things out. You could swap out WordPress for like a Ruby on Rails framework or for Django or whatever you want. And you could swap out Apache for Nginx or for some other server backend, whatever you want, right? In fact, I'd prefer to make the comparison that we're more like Nginx than Apache because no one really likes Apache. IBM can be Apache. Anyways, so I don't think I was supposed to say that. So the analogy in this example, basically that Eris is like an application level platform where they're agnostic to the underlying consensus, but they have opinions about what the application should look like, right? Which is very much like WordPress. WordPress is agnostic to the underlying server, but have opinions about what your blog should look like, right? And on the other hand, Tendermint is this lower level, server side or more server oriented platform that is agnostic about the applications you run on top, right? But is opinionated about the fact that you use Tendermint and not something silly like proof of work. Just like the same way Apache is, a server that says you're using the Apache server model and not something intelligent like Nginx. Right. So hopefully that makes sense and that sort of puts things in context. And basically the way this works is that when you want to actually go and run a Tendermint blockchain with some application on top, Tendermint itself doesn't come with an application, right? If you just try and start a Tendermint node, it'll crash and say, hey, I don't have an application to talk to, right? So you have to start an application that Tendermint can talk to, and it should be the only thing talking to that application should be the Tendermint node so that it can drive the state changes when there's consensus on new transactions. And if there's questions, we can talk about them. Right, so here's maybe a little bit more of a clearer picture. So if this is like our network, each of these is a node, and the core is one process running on the node, and the app is another process running on the node, and they talk over a socket. And they use a very simple protocol to communicate. We call it the TMSP, the Tendermint Socket Protocol. It's very simple. It just defines a few messages, basically the basic messages we need to have a blockchain application. So essentially they are append TX, so that we can take transactions from the consensus and apply them to the application state, and get hash, so that the consensus can say, hey, application, what's the current hash? I need to put it in the block, right? And that's basically it. There's a little more subtlety, but at the end of the day, users submit transactions, they get put into blocks, they get sent to the application runs them against the state, and then the core asks for a hash, the application returns it, and we move on, right? So, in the core, we have things like the actual consensus algorithm, the mempool, that's where we store the blocks, which handles all the P2P, and then in the application, you have the actual state storage, right? Which could be something like the UTXO set in Bitcoin with all the scripting language, or it could be Ethereum's virtual machine with its account system, or whatever blockchain application state you want. But we're trying to make a very clear distinction between the underlying consensus algorithm and the applications that run on top. Right. Cool. So here's sort of a step-by-step of sort of what I just said. A user sends a transaction to Tendermint Core using HTTP. There's another message I didn't mention called check TX, so that the core can then say, hey, application, is this a legit transaction? The The application will say, yeah, this is legit. It'll say, no, this is crap. Don't keep this around. And then it'll check a bunch of transactions. Then it'll make a block with those transactions like usual. It'll pass the block around the consensus. Everyone will say, yeah, this is a legit block. Let's commit this thing. And once it's committed, then we'll go and actually run the transactions against the application to get the new state. And then we can say, hey, what's the hash, right? It's a very, very simple system, but incredibly powerful because now it allows us to write applications in arbitrary programming languages. So we can write them in Go, we can write them in JavaScript, we can write them in Python, we can write them in Haskell, we can write them in whatever you want. And we have examples of the same application written in multiple languages, and we can show you that. Jay. Keeping you on your toes. Pay attention.
So before we get into demos, I just want to talk a little bit about where we're going as a company and what you guys have to look forward to that we're building out now. And this will be available later this year, and we're very excited about it. The whole thing about our company and what we're making is making it simple for you, the application developer, to build, deploy, and manage your blockchain. So with that, we are developing, the first thing is TMSP, which is the architecture. It makes it easy for you to build your application. We have a tool called Mintnet. If you go to our GitHub account, github/tendermint/mintnet, it's a tool that uses Docker Machine to launch a blockchain onto any cloud provider. So Docker Machine supports EC2, DigitalOcean, and even your own cloud machines. And you can use Mintnet, which is just a wrapper around Docker Machine calls, to set up a whole blockchain, all the Genesis files, all the private keys, the validator keys, and it'll deploy it onto the cloud, and you can manage it. It's best used for, we use it for development. We use it to launch a blockchain onto the cloud and make sure that everything's working. And soon it'll be fleshed out to be a full tool for managing a live blockchain, but for now, it's a development tool, so please use that. But the end goal here with what we're building is a UI for managing all these applications. Now, so Tendermint has this concept of validators, as you know, and there's a set of validators that are designated to commit blocks on a blockchain. That validator set is it comes about through, you can create a validator set however you want. It may be a consortium of banks. It may be that they posted collateral in-chain to become a validator. You can have a validator set however you want. But once you have a validator set, it makes sense to consider letting that validator set run multiple blockchains. And so this is how we might do scaling. If you have, say, an Ethereum blockchain and it can only handle 10 transactions per second, right, that's a problem. So what do? You just have each validator have enough compute capacity so that it can run a parallel chain. So you can run as many Ethereum blockchains as you want. And to manage that, and to manage the consortium, and to manage the proposals, the whole governance system of proposing a new blockchain, or the launching of it, or the destruction of it, or the configuration of it, even to manage the change of validator sets, we're going to need an intuitive UI for people to use, and that's what we're building. We're building the whole platform and the UI so that anyone can be part of the consortium and manage their blockchains. With that, let's get into demos.
Sweet. How are we on time? Yes, that's how we are?
Yes.
Good. Yeah, yes is a time now. That's great. Time is at yes o'clock. Cool. Any questions before we dive in? Yeah.
You don't run any public blockchain, right? So it's all like private.
Well, we could. I mean, there's nothing stopping us. Are you going to get in the way? Are you going to try to stop me from running a public blockchain? Yeah? Let's take this outside.
What would it mean to run a public blockchain in this private space?
It's a good question. I'm not sure what you mean in this private space. I mean, if we, say we started a chain and we want to have a bunch of validators out, we could take everyone here. We could start a chain with all of you. Like we could actually do this if you guys want to do this. That would be awesome. And we could give everyone here some voting power, and then we could all run Tendermint on our computers, and then we would have a live blockchain, and we could bring other people in and so on. Whether or not it's public is a debatable question.
It's like a country has can allow immigrants in or not. Is a country permissionless or not? It really depends on the government.
Great example. What's up?
Okay, so
Last question before we move on to demos.
Okay.
okay, so
Thanks.
not all of the nodes of the blockchain is required to run the same set of validators, right?
Yeah.
Will they still accept transaction without knowing what does it mean on application level?
Sorry, what do you mean?
For example, I will submit a transaction that is invalid for an application that this specific node doesn't have installed.
Oh yeah, so there's this checktx message, right? So when you submit a transaction, the core will send it to the app and say, hey, is this legit?
But what if the core doesn't have this app installed?
So it'll send it to the app it does have installed. If it doesn't have any app installed, then it's not running Tendermint, right? I mean, there has to be at least one app for it to be doing
How the
anything.
network can figure out that it's not malicious?
Let's move on to demo. We'll take it.
Okay, cool. Demo. So, right. I'm gonna put this down. I talk loud enough, right? What? You want me to do this again?
Yeah, do another song.
I would, but I recently wiped my drive and they're all in Guelph. Guelph's this awesome town in Ontario. You should all check it out and move there. It's awesome. What am I doing? Demo. So, okay, great. So I have this, I set up a little folder here. Let's clear everything. Right. So this is going to be a simple demo, but it'll show the pieces of the set. Oh, we were going to do TMSP first, right?
Yeah.
We should do that first. Okay, cool. So I'll do that first. So we have a couple demos. One is just like something simple to get your feet wet, and then one is something awesome to get you really wet. Okay, so we use Go because we love Go. It's a beautiful language. Installing stuff is super simple. You just go get github.com, Tendermint /TMSP is the repo, and then ... will go and install everything. I already have it, so I don't actually have to walk through with it. But that will install a couple default applications for you. One of which is the dummy. The dummy is quite dumb. It doesn't really do anything. It accepts transactions, stuffs them in a Merkle tree, and that's about it, right? And so we have a simple tool for working with your application to make sure it works within Tendermint and TMSP. And that is the TMSP CLI. So if we type TMSP CLI, that would also have been installed with that last command I run. It shows you the options. So these are really, where's my mouse? These are really all the messages that TMSP supports, right? So the main ones for the blockchain are really these three, right? So these are the ones that are always being used live, and then the other ones are a little more administrative. Echo is just to make sure things are working. Info dumps some info. Set option is for setting like configuration options or different parameters. And then query is just so that we can see that things are working, right? And so we have this console that you can drop into so you can do sort of interactive commands. It's very simple. If you just hit enter, it'll show you that list again, right? So we can say, echo hi. We should see that it says hello. We can see some info. Our Merkle tree is currently empty. If we get a hash, it's also currently empty because there's nothing in there. So now we can go append a transaction. Let's make a very simple transaction, ABCD, right? It's happy, it didn't return any error. Now if we hit get hash, we should see, oh, now there's a real hash because we just stuck something in a Merkle tree, so now it has some root hash. And if we go and query, we can go ask it, hey, what's the value stored at ABCD? And it's just storing the same value we gave it. For this app, we also can do something simple like, EFG equals I'm awesome. And then if we go query EFG, it will tell you what you already know, namely that I'm awesome. So, very simple, but you can use this to help sort of debug your application without having to worry about the underlying consensus, right? And so we have a tutorial. If you go to tendermint.com, click on tutorials, it'll walk you through doing this. And we have a few different apps. And we have another app besides the dummy, is called the counter app, where basically every transaction has to be an integer that's one more than the last one. And we've implemented that in Golang, in JavaScript, in Python, and I'm working on a version in Haskell because I wanted to learn Haskell. And so you can use all of them, interchangeably, basically. You should be able to use them on the same network. But it just goes to show the power of this new architecture where you can really write your smart contracts, your applications in arbitrary programming languages. Okay, so that's the application on its own. That's not that interesting. We want to see it actually run on a blockchain, right? So I'm going to kill it. I'll start it again. It doesn't save its state because it's just a dummy. And now we'll run a Tendermint node. Oops, let me just make sure there's nothing here. Just go Tendermint init. It'll just lay some basic stuff for me, and then I can run a Tendermint node. And, oh yeah, sorry. We will change this. You just have to set fast sync to false for now. We'll fix that. Basically, there are two methods of syncing up with a Tendermint blockchain. There's using the normal consensus, and then there's the so-called fast sync, where you just quickly check the headers instead of going through the whole consensus process. And so, this is very lightweight. All we're seeing is that we're just committing new blocks, committing new blocks, committing new blocks. And so now, if we want to send a transaction, we have a very simple API. We can just curl it. We can go localhost 46657. I'll show you. I'll just show you in here because it's a self-describing thing. So these are the endpoints available right off the bag, and you can use them for debugging or for actually sending stuff. These ones don't take any arguments. These ones do take arguments, right? So I can just copy this, say, paste it here, and then fill in a transaction. Let's say ABCD, right? Okay. So it returned. It's happy. There's no error. And now I can use the TMSP CLI to make sure it worked, and I can just go query for ABCD. It didn't work. Oh, it's capital. No. Anyone? Slashes are in the right place.
But the data is known in their.
Yeah, that's just the return. It doesn't return anything. Oh, it's the hex. That's what you're saying, right? Yeah. Okay. So we have to work on some formatting things, but basically, if I do this, it should work. And say 2 hex. Hi, mom. Now if I TMSP CLI query, hi mom. This isn't promising. I swear all this was working earlier. Jay, what do we do? Quick. Oh, there it is. Okay, so it just took a second, but it managed to show up eventually. And so if we look back here, we'll see somewhere up here that got committed with a transaction. There it is. So we just have to wait for it to commit, and then it shows up, right? Yeah, so it worked. Right? I can query and it shows up. Hi, mom. Hi. Okay, so that's very simple. This is just one node running on one computer. We can send transactions. The transactions are trivial because our application is trivial, so there's no signatures or anything like this. All we're doing is passing data in, stuffing it in a Merkle tree. But again, just for getting your feet wet, it's a nice application. Okay. So that's clear. Let's do something more interesting now, where we'll actually go and deploy this thing in the cloud. And so what we'll do is we'll go set up a network with 4 validators. We'll start the dummy on all of them, and then we'll start sending thousands of transactions at them. We'll see the blocks fill up with transactions, and then we'll start taking down nodes and showing that if we take down 1 node, it'll still work. If we take down 2 nodes, the network should now halt because it always needs at least 2/3 online. The transactions will build up in the mempool, and then once a node comes back online, it'll start committing and clear out the mempool, right? Just like what happens with Bitcoin. So wish me luck. I don't know. Okay, so I have a couple scripts here to make my life easier. I will show you what they look like. So here's our launch script. It's quite simple. Basically, we initialize a few directories. So this mintnet and init will just initialize some directories for us with the information we need. I have some machines. So we use Docker Machine. Docker Machine is great. It allows you to just easily deploy nodes in the cloud, right? So you can go Docker Machine create, and it'll set up a bunch of nodes for you, and then display them. So we're going to work on these guys, test 1 to 4. So they've already been created, because creating live is probably not a bad idea, because it like always fails and you have to redo it. But don't worry, Docker's working on it. And then we have a very simple DSL, so that this mintnet will understand that this means, okay, test 1, test 2, test 3, test 4. We're going to deploy a blockchain on all of them. We're going to use the dummy init script, which is right here, that basically just says, go get the dummy app, check out the right branch, install it, and run the dummy. Okay? So that'll initialize some directories, and then when we run start, that'll actually go and start all the processes on every machine, right? And that'll take a couple minutes, and we'll see it scroll by. And then we go and start our net monitor so that we can monitor all the nodes at once, right? So I'm going to go launch this. This will take a couple minutes to complete. We can watch it scroll by. It's very pretty. If anyone wants to ask a question while this is happening, floor is yours. Yes.
I got a question. So earlier you guys said that Eris uses your product, Tendermint.
Sure.
But if I recall correctly, and you may not be that good, this was a long time ago, Eris forked Ethereum and then started making modifications to their Go clients.
Right.
Don't they use Ethereum?
Okay, so disclosure, I still work at Eris. I'm a lead developer there. I'm transitioning to Tendermint, basically for the sake of, I was looking at these businesses as if they were code, and it seemed like some refactoring needed to happen, and I needed to move this human over here for a little bit. So that's what's happening. So initially, you're right, Eris forked Ethereum and did this crazy thing where we pushed the consensus rules into the Ethereum virtual machine. But the Ethereum virtual machine is so bloated and slow that was not a good idea, right? So what ended up happening is last year in January, I came to San Francisco, and I met Jay, and we talked about Tendermint, and I was like, this is what we need to use. This was before we had done this architectural separation. So Eris basically retooled on top of Tendermint, and that's where ErisDB, the Eris blockchain, is basically a Tendermint blockchain with additional application state, including the Ethereum virtual machine.
So is Tendermint basically built on top of Ethereum, or are you guys basically running it?
No, Tendermint's an independent engine, right? So it's its own consensus protocol, its own peer-to-peer layer, and then you can take arbitrary application states and put them on top. So recently, I forked Go Ethereum and put it on top of Tendermint. So you can use all of Ethereum's tools and the Ethereum development ecosystem on top of a Tendermint backend.
Okay, so with Eris though, you have Tendermint in the middle, but then you still need some kind of blockchain provider.
Tendermint is the blockchain provider, right? Yeah. So Tendermint actually provides the thing that gets consensus on blocks and commits them into a blockchain.
So you can act as a blockchain provider, or you can take somebody else's blockchain and wrap it.
Sure.
Thanks.
Cool. I'll continue, and then there'll be more time. Okay, so everything has started up. We see, done launching Tendermint network. Now we've started our network monitor. We do everything with simple HTTP requests. So I'm just going to show you. What? Yep. Okay, so the net monitor knows about one blockchain. It's called My New App. We can go look at it now. Get chain ID. My New App. Oh, beautiful. So this is just some summary information at the bottom here. It basically keeps up with the height. The height is changing and tells us some basic information. We have all 4 validators online, so we're at full health. And basically what we're going to do is we're going to start bombing this thing with transactions, and then we'll start killing nodes, show you how this changes, how the blocks stop being made, and then bring it back online, right? So to do that, I'm going to start a local Tendermint node. and that's going to be the thing I send all my transactions to. So basically, I'm just going to copy in the Genesis file we just made, and then I'm going to start a local Tendermint node and connect to all the Docker machine IP addresses we were looking at before, right? So if I start that, that's fine. There's the dummy you can see. Now it's catching up, right? So it should be all caught up. And now it's synced. So this node that I'm running on my laptop is not a validator node. He's just synced up with the blockchain, right? And there's 4 validators in there in the cloud, and they're actually the ones committing blocks. And this guy is just keeping up with them. He's just listening in, right? But we're going to use him to broadcast our transactions to everyone. Okay. So we've got another script here for sending transactions. It looks like this. It just grabs some random data, random value, and then it goes and broadcasts that key value pair, sleeps for 100 milliseconds, and does it again. And we'll do that 10,000 times. So if we run this thing, it's just bombing it with transactions. If we go here, we'll start to see that the transaction throughput is starting to tick upwards. At any time, we can look at the unconfirmed transactions. So we can look at our local guy, 46657, unconfirmed TXs. So currently we have 13, and then they clear out when they get put in blocks. So we're constantly generating more. The mempool fills up, and then it gets cleared when a block comes. It fills up, it gets cleared when a block comes, and so on, right? Everyone with me? Yeah? Anyone confused about what's going on? Tell me, and I'll happily clarify. Okay, great. You guys are great. Okay. What? Okay, so now let's kill nodes and prove that, Tendermint's actually worth something, that we can kill nodes and the whole thing won't just crash, right? Yeah, let's fuck shit up. Woo! Biggie Smalls. Okay, so I've got this command here for killing the guy. Okay, so all this is going to say is we're just going to blow the whole thing away on machine test 1. It's just going to takes about a minute because Docker is like really slow sometimes, but blame Docker for that, not me. So this thing will go down, and once it goes down, we will see that we're only going to have 3 active validators, right? But 3 of 4 is more than 2/3, so our blockchain is going to be fine. It'll keep going. Oh, it's going to take a second. Where are we? This guy taking his sweet-ass time. Ooh. That was a fake yawn. No, it's done.
So it knows the state of the network, it knows the maximum node, so when node starts dying off, it's comparing against the maximum.
Yeah, that's right. Look, so now it knows, oh, one of the validators is gone. So we're no longer in full health because we lost a validator. But we're still healthy because we're still committing blocks, right? So the block height is still going up, and we're still crunching transactions, right?
How do you remove a node permanently?
So I just took him down. He's gone. Oh, you mean how do you reduce this number?
Yeah.
Great question. We currently don't support that, but we're working on it. So we used to support it, and then we got rid of it when we did this re-engineering of the architecture, and now we're going to bring it back. Because it's obviously important that you can change your validator set.
Same thing applies for adding nodes to the
Same thing applies for adding nodes. And of course, being Bitcoiners, someone will say, oh, but censorship resistance, and you're right, and we have like real world means for dealing with that. Great, so this is pretty clear, not that exciting. Oh, we lost a node, it still works, that's great. Bitcoin loses nodes all the time and it still works. Okay, let's kill another node, right? So now half of our network is gonna be down, right? Half of the network is not enough to commit blocks in a Byzantine fault tolerant algorithm. So when this guy goes down, we're gonna stop increasing in height, and that's gonna be it. The mempool is just gonna start filling up, right? So if we go look, right, so he's down now, and the mempool is just crunching. So if I go dot result here, dot n tx's, oops, sorry, no, just n. Let's get rid of all that junk. Great. So mempool filling up, getting bigger and bigger. We're not making blocks. I can prove that, right? We're stuck at 253. We'll be there for a long time. because the validator's down, right? We only have 2 of 4. We're no longer healthy, as you can see, right? And yeah, that's kind of unfortunate.
What's the difference between full health and healthy?
Full health means everyone's online. Healthy means you're making blocks, right? Healthy means at least 2/3 are online, right? So, you know, our mempool is getting pretty big. We could wait until it gets so big that all the nodes crash, but then that'll ruin my demo, so I won't do that. Okay, so what I will do is now restart one of the nodes. Let's say test 1. One thing I have to do, though, is tell it who to connect to. So I go seed machines, and again, we can use this fancy DSL, right? And so this will take a couple minutes, so let's take a question.
So did I get it right that situations when nodes are popping up and like disappearing is like not kind of clear? Because I mean it's one of the key values of Bitcoin that nodes can show up and disappear at any time.
Sure.
So it's not working.
It works here if they're part of the validator set. So the difference here is that the validator set has to be registered. So if you have a validator set of 1,000 nodes, then any 300 of them or so can go up or down as they please.
So what
right?
it takes to launch a node and connect it to the existing network? When I stumbled upon some network, I want to launch all nodes. What should I do?
You want to join it as a validator? Yeah.
Like a full node.
Right. So you can start a full node and just sync up no problem, just like the one on my computer, right? So the node on my computer is not a validator, but it is synced up with the network, right? So there's 4 validators plus 1 node, which is my computer, right? So doing that is trivial. It's very easy. You just start it and say who you want to connect to. Like I was saying before, though, if you want to actually become a validator, we haven't implemented that yet within the new architecture. We used to have it. We got rid of it so that we could retool simply, and now we're going to bring it back.
So what is the difference? Will I not be able to broadcast transactions? Or?
You can broadcast transactions, you just can't validate them.
Talk about bond transactions.
Yeah, so it used to be the case. So Tendermint, the way it used to be structured, everything was in one app, or everything was one process, right? So the consensus, the application was all together, and there was transactions, let you move tokens around, whatever, and there was a special transaction type called the bond TX. And so if you have some tokens, you could send a bond TX, and that would bond your tokens, and then you would become a validator. And then if you fuck around, you would lose those tokens. They'd get slashed, right? So we'll bring back that mechanism, but we're going to do it in a more flexible way that works within sort of alternative governance structures. That's really the goal.
So will the node kind of download validators from some external source, or how do I get validators if I wanted to become a validator?
If you want to become one, on a network that already exists. Right. So you would sync up with them. You'd have to know some IP addresses, right, of nodes that exist. You'd sync up with them, and then you would send, for example, a bond TX, and you'd say, hey guys, I want to be a validator. And they'd accept that transaction, and now you'd be a validator. And if you don't validate, you'd get in trouble.
Do I have to install all applications that exist in the network?
No, just one. Just the one you want to do for. Okay, so it finished launching. That's good news. Our dude's back online. We're healthy. We're making blocks. So everything's legit. Let's check the mempool. It's been cleared out. It worked. This demo went amazingly smoothly. Round of applause for Tendermint. Yeah. All right. So, that's that. You can mess around more. We can bring up the other guy and get back up to full health if we want. Yeah.
You might have mentioned this earlier, but how fast do you generate blocks?
Within a second. Yeah. So, I mean, if you look here, the blocks are pouring in. Basically every second we're getting another block. And you see it tells you how many transactions they have. 35 transactions, 10, 11, 10, etc. So, yeah, the block size is arbitrary. It's currently not capped. So, you could DOS us. We're aware of these things, but, we're in development. What's up?
Can we up the block time? Because if it gets large enough, I'm pretty sure orphans lost.
Okay, so great question, because it betrays a misunderstanding. And so the question was, can we increase the block time, because if it's too fast, we'll have orphans, right? Now, there's no concept of an orphan in Tendermint. And it's a very important thing to understand. Because the way Tendermint works, the validator set. You know that there's 4 validators, right? And they take turns proposing blocks. So at any given time, there's only one person who's supposed to be able to propose the block, right? And if he's not online, everyone who is online has to sign off on the fact that they thought they were going to receive a block, they haven't, let's move on. And then they'll go to the next proposer, right? So we have this round-based mechanism for the consensus where, one guy is supposed to propose, he's the only guy that's allowed to propose, and then everyone comes to consensus on that block before the next block can happen. And if that guy's not online, they can skip him, but they have to have consensus on the fact that they're skipping him, right?
You have another part of the presentation or doing questions now?
Do we have another?
Yeah, what?
Oh, you want to show Blackstar?
Yeah.
Yeah, cool. Okay, great. So I will can all this. Jay just needs a browser. Great.
This is a sample application written on TMSP, written in Golang, which is a simple cryptocurrency. So it's 300 lines for the main application. It's this file. You can see it here. And it's a full cryptocurrency. Very simple one. And
You increase the font?
yes. Can you see that? Okay. So I'll show you what's going on here. It's just a cryptocurrency. So it just has a single token, and there's multiple inputs, multiple outputs. It's not quite UTXO. It's because you can use the same account multiple times. There's an incrementing sequence, a nonce, we'll be building this out so that it's more usable. But here we're showing it for the sake of demonstration. So we have libraries set up so that all you need to do is basically implement an interface and fill out the methods. And the wrapper that we've created in Golang, we've also created one in JavaScript, and we'll be building out in other languages too. It takes this class, basically it's a class like an OOP class, and creates a whole TMSP application. So here's info. You can go to, if you go to TMSP CLI and ask for info, it'll run that, and that's what it'll return. Set option, that's administrative. Let's ignore that for now. So there's two main functions, or three main messages that need to be implemented. One is append TX, you can see here. The other is check TX, and the other is get hash. And I'll just go through these. So you see that the logic is pretty simple. When you append TX, it's just a sequence of bytes. So you can use any encoding scheme. It could be protobuf. It could be anything at all. And you can use any public private key encryption system. We really leave it up to you. And in this case, we're using an encryption scheme called Wire, which we created. But I'm just using it because I'm comfortable with it. You validate the transactions, and if the transaction is not valid, then you return a code, a special code returned by this function here that says that the transaction is invalid, and that's the code that the user will see on the blockchain. Let's see, and all this does is it loads the account, it executes the transaction, and then it stores it. So so where is it storing it to? So when we first created this architecture, it was missing a storage component, a data store. And we've created that now. We call it Merkle Eyes. Merkle Eyes. I can show it to you, but it's like LevelDB or Redis. It's a key value store, except it also handles Merkleization. So when you say, get me the hash after a bunch of updates, it'll compute the hash for you, and you can return the hash from your application. So here, when you do store accounts, you pass in the Merkle Eyes client. I'll show you the implementation of that.
LevelDB is flat though, it just have keys and values, whereas Merkle tree is hierarchical, right?
Yes, Merkle trees are hierarchical. So we do provide, we do handle the tree and all the crazy hierarchical node stuff, but the interface to users is just a key value store. So we hide away all the complexity. It looks like a basic key value store to you, but we do the Merkleization. let's see, store accounts. So here is, just calling the Merkleized server and you're saving accounts. Pretty simple stuff. Another thing to note here is that when the core, Tendermint core, asks this application for the Merkle hash, which it'll include into the block hash, you'll see that all we're doing is really just asking Merkleized for the hash and passing that straight through. Yeah, so that's how you build an application, and you can build one in 2 days, apparently, and it's 300 lines for a basic cryptocurrency application. So check out our examples. This one's called Blackstar, Tendermint/Blackstar. There's another one in JavaScript called NomNomCoin, and we'll be building out more examples for you to follow, and that's how you get started.
Okay, that's awesome.
Thanks.
Thank you. All right, we have some time for questions.
Please wait for the mic.
Good job. Yeah, you too. Yeah. This guy. You're banned. We're censoring you.
I was trying to do similar thing earlier.
Sure.
So I wanted to build on this guy's question over here with the waterfall, right?
Yeah.
So
Use the mic.
I'm guessing basically you're doing something similar to what Dash does. It has leaders, it has elections, so on and so forth. It's
Yeah.
built off a chubby zookeeper.
That's right.
So aren't you afraid of like centralization that way? If a majority of nodes are in a single region, if somebody spins up a very vast majority of nodes, you stole my question, I'm gonna steal your second question. But you get what I mean.
Yeah. We get this all the time. I don't know if you've noticed, but Bitcoin's pretty centralized. So, at the end of the day, it's like there's something called reality. And, humans and like human relationships. And I know like people in the crypto world don't like to be able to have to think about those because they don't fit in the models. But that's like who actually uses the stuff. Yeah?
For Bitcoin, the block time is large enough for you to put it in China and the US combined. But if 500, let's say, being in Pakistan, I've seen things go up to 700, 800.
Sure. Yeah, I mean, we can adjust the block time, no problem. Yeah, so like right now, that 1 second is actually high. There's a period in there where the nodes are just waiting for other nodes to catch up, right? So really, we could commit blocks in like a few hundred milliseconds probably, right?
Yeah, if it's in a single data center.
Yeah.
Like it would be in Wall Street.
Right. Great question, though. We'll get to you. Hey.
I was wondering about the number of transactions. So I was thinking about like proof of stake algorithms like Ethereum, Casper, Split. I'm thinking the bottleneck is the validator's hardware, right? So how fast they can process transactions from the AVM. And I was wondering what's the inherent bottleneck here. So is it like network latency, something in the protocol? Okay.
Yeah,
ahead.
I'll take it. There are, sure. There are several bottlenecks, and I'll go through them and I'll try to describe the characteristics. One is the network latency and the number of validators. So in order to commit a block, you need basically, if the number of validators is n, 2 n squared numbers of signature shares before you can commit a block. So if you have 1,000 validators and you use ed 25519, that's fine. But if you have 100,000 validators, it becomes a problem because it's n squared. That's one. Of course, if the network is bad and you have a global blockchain, then like we mentioned, that's another problem. But if we discount those and just say you have like 100 validators and the network is fine, then we're talking about the other bottleneck is how many transactions per second the application can handle. And if you use Tendermint and TMSP and plug in Ethereum on it, then you'll probably get a little more performance out of it because you don't have to undo blocks, and it's just a straight line of commits. So that's that benefit. But the EVM, and depending on the application, if it's slow, that's your limitation. Right.
Yeah, you mentioned earlier when you were showing the interface, I think, you mentioned something about validators running multiple blockchains in parallel.
Mm-hmm.
Is that something with Tendermint scalability or one without?
Sorry, what was the last few things you said?
You mentioned something about running several blockchains in parallel.
Yeah.
So I was wondering what that was about.
Yeah, so we think that, the thing about blockchains and what makes it really secure, and safe is that it's auditable by like anyone. Anyone can sync up to a blockchain and verify its history. And so we took that concept and we said, okay, blockchain is just whatever a computer can do. A blockchain, a single computer on a typical application can handle like 1,000 transactions per second if it's like a cryptocurrency, thing. But that doesn't scale if you need 100,000 transactions per second. So we'll scale it out by running multiple parallel applications under the same validator set. And if you do that, if you say, these blockchains are running under the same validator set, they share the same validator set, but it's the same application, then you can think about ways to have these blockchains interoperate. You can use like the Interledger's Interledger protocol or
Hyperledger.
Hyperledger. Yeah. Well,
The IBM thing, right?
no. You can use all kinds of protocols to transact between blockchains. And I know that you're working on such a thing yourself. But there's other ways to do it too if you have a closed system like a single platform with a single validator set. So we'll explore all of those.
So if I get it right, your consensus algorithm requires a network to go through each validator sequentially and let him broadcast transactions, right? Which means that all validators should stay in sync all the time because eventually each of them will get this right to vote. Which means that the throughput of the network is limited by the capacity of the fastest validator, right?
Yeah.
Don't
The
you
slowest.
think it's the slowest.
Yeah.
Don't you think it's a bottleneck, especially in distributed networks when you have nodes all across the globe?
Yeah. Yeah, man up and get a better machine.
Okay, but wait, if you let anyone connect and become validator by connecting some slow machine, and
Right.
will slow down the entire network.
Well, okay, so you only need 2/3 of the validators to commit a block.
Right.
So if you have, say, 10 validators and you have 2 slow nodes, that's fine. The 2 slow nodes don't do anything. It's as if they're down. But over time, if you have a proper governance system and a cryptocurrency, say, and you have, say, 100 validators, and you find that one of these validators is very slow, the governance system should say, this validator is no good. Let's take him out and replace him. That's one example of changing the validator set. But to answer your question, it's not the slowest validator that's the bottleneck. It's the bottom 1/3 tier.
Right.
Well, do you have a? Okay. So earlier at the beginning, you mentioned about punishing, bad nodes. Can you describe a little more of that mechanism? Meaning, is there a state that's kept somehow in the network, so you know this node is bad? How do you identify the bad nodes? Do they have any kind of ID, so you know they're bad when they come back?
Yeah. So I can answer that.
Cool.
Yeah. Okay. So there's all kinds of things you can do, even for a basic cryptocurrency on Tendermint for validators. There's all kinds of things you can do that are bad. There's all kinds of marginal things that are maybe considered bad too, such as like censoring transactions. But let's not talk about those. Let's just talk about what pertains to the consensus algorithm. So some of the things you can do that are bad are you can withhold transactions, you can try to delay the process, you can double sign. So what that means is every validator is signing something for a given for a given height, which is a block number, and the round. Usually the round is 0, but sometimes it's round 1 or 2. If you sign 2 different block hashes for the same height and round, that's double signing. Right? And that's trivially discoverable because you can compare these 2 signatures and say, you signed 2 different block hashes for the same height and round. Okay? That's one thing you can do. Another thing you can do is you can unlock when you shouldn't have during the consensus process. This is a bit trickier, and there's a process for discovering that. Currently, the best way to do this is to say, if once there is a fork, you ask the whole system, show us all your votes and justify them. Show us all the things that you've seen that caused you to vote to lock or unlock in the way that you did. And if you're an honest validator who did according to the protocol, then you should be able to justify yourself. If you can't, then there you found the culprit. If there is, say, a fork in the system, you will always find at least 1/3 of validators who had either double signed or cannot justify their votes. So that's the current iteration of the Tendermint consensus algorithm. In the next version, we're going to make it so that every commit implies that finding double signers is immediate. And that's just the next thing we'll work on eventually.
This guy, Matt, has a question.
So, your API, the validation part of your thing has to implement has only 3 calls, right? You said it has the get Merkle group map, check a transaction, and compare it based on the current state, and then append the transaction state. So this implies that because you have no kind of reverse transaction out of the current state, how do you handle memory pool consistency? How do you check that when you're checking each transaction in the memory pool, you are checking them against the state of the total of the memory pool and not
Yeah.
outside of that? And then if you're doing that, then can you allow for conflicting transactions from mined by a different participant in the network to be removed from your state, already added to your state because it's in your memory?
Yeah. So that's a fantastic question. The question is, we don't allow for, there's only append, there's no revert, right? And so how do you handle the situation where like a transaction that's getting committed and was checked and was found to be valid through the mempool gets committed, but it's wrong. So we used to, the first time we created the architecture, the TMSP system, we did have a rollback message. And but we found out that it's much easier for the application developer if they don't have to worry about rollback. So what we've done is we said, okay, the transactions that are committed through Append TX and TMSP are the transactions that have already been committed. But being committed doesn't mean that the transaction is valid. It's entirely possible for a block that was committed with the transactions to, once they push the transactions to the application through TMSP, that the response back is that code saying that the transaction is invalid. In that case, the response codes will get included into the blockchain so you can tell which transactions were actually valid. If the application is deterministic and everybody's running the same code, then everybody should come up with the same result. So the idea is first you decide on the order transactions, and then you figure out which transactions are invalid later.
So you don't actually get transactions confirmed, quote unquote, for at least one more block?
That's right. The state hash goes in the next block.
Mm-hmm.
Right.
Hey, I was wondering if you could tell us a bit more about the ICE thing and how you go from having a flat key value store to a hierarchical, memory efficient Merkle tree. And I'm also wondering, like, doesn't that kind of invalidate the good parts of both Redis and Merkle trees because you're doing both of them? With Merkle trees, still it's slower, but you save a lot of memory. And with Redis, key value stores, it's key value stores. Really fast and really stupid and simple. The other thing that I wanted to ask was, so Ethereum takes language X and then transpiles it into EVM code. What do you guys do? Like, what's your transpiler system like and the ice thing?
Okay, I'll start with the Merklei's. And we can do that.
Sure.
Yeah, so about Merklei's, it's just the API that appears to be flat key value store. But when you append when you set a value to a key, and there's already an existing data in Merklei's, what's happening when you set a value to a key is it's using the AVL tree algorithm. It's a self-balancing algorithm to rebalance it, and when you can do that multiple times, and every time it's log of n in compute complexity, and then when you ask for the hash after multiple of those modifications, it'll efficiently compute the hashes for the inner nodes that are new, that have been modified. But the inner nodes are not accessible to the end user. Right? So we'll have an API so you can even get the proofs, the Merkle proofs from this data store. But it's not about the inner leaves. The end user doesn't see that.
So basically, you're saying you save history on how keys value.
We don't save the history.
You have a record of, this is what history was.
We don't garbage collect.
Yeah, so, right. So actually right now we don't garbage collect the Merklei's. So all the history is there. All the
It's immutable,
yeah,
right?
it's
So
immutable,
everything
yeah.
persists. Yeah.
Right. Yeah. So you're right. But once we do the garbage collection, then even once you set a new value on top, the old value will disappear. And about performance, if you keep everything in memory, for example, and you have like 1 million key value objects, then this can handle like 10,000 or 5,000 or something like that transactions per second. It's pretty fast. Mm-hmm. Okay.
Yeah, as for your other question, what's our analog to like compiling to the what's that? Oh, sorry. Your other question was about what's our analog to compiling like down to EVM bytecode, right? So using this new architecture and talking over a socket, you can write your application in any programming language you want. So you can write your own EVM or your own virtual machine and compile down to that, or you can just use a normal programming language like a normal human being, Python, JavaScript, whatever you want. So there doesn't have to be a compilation process if you don't want. If you just want to write the app and have it be a fixed app, like a simple cryptocurrency, or you could take Bitcoin as it stands, any of the implementations, take the application state and put it on top of Tendermint, that's fine, right? If you want something where you can deploy new functionality live, like Ethereum allows you to do, then you need some kind of virtual machine and some kind of bytecode that will run in it, right? One of the things we're looking at is having a model where you can actually like put up new Docker containers, right? So the application is really something that just manages many Docker containers, and then if you want to deploy a new functionality onto the chain, really all you have to do is deploy a new Docker container that could have, the application again written in an arbitrary language. There are, subtleties about that related to non-determinism and the halting problem and so on, but we're working towards sort of practical solutions to those.
All right, 2 more questions and then we have to stop.
2 more questions and then another song.
Sing the song. You sing that song?
This one? Yeah.
How do we prevent someone from pretending to be 1 million validators and in this way acquiring the majority in the network and acting and slowing it down? So someone can start a fake node that will act like 1 million validators that will get accepted by the network and he will get the majority.
Yeah, so I mean, it's up to the validators not to accept 1 million new validators. So it depends on the system, right? We've built a platform for deploying blockchains. The actual configurational and governance state of the blockchain you deploy is up to you. And it's up to your governance mechanisms to prevent that. If you want to use proof of work to do that, all the power to you, right?
So it assumes some KYC process for validators.
Well, you can, but another way to do it, which was the old Tendermint method in the old white paper for Tendermint, is with a bond transaction. So in that case, in order to become a validator, you have to have coins. You might specify a minimum number of coins that you have to bond, which already limits it from 1 billion to just a handful of people who can bond, who have the coins to do so. There's all kinds of ways you can limit that.
Cool, so it sounds like it's an awesome modular network, and you guys should.
Are you guys hiring or something about some kind of self-pay?
Yes.
Yes, we get requests for projects to be built on top of Tendermint and TMSP, and we're hiring. We're hiring for awesome blockchain developers, system developers to help out, build out all these applications. And also, if you have your own software company and you want to work on blockchain applications and you don't want to get hired by us, that's fine too. Just talk to us and we'll give you work to do.
All right, thank you, Ethan and Jay.
Oh, just email us. Just say hello at tendermint.com.